Day 134 notes, pre-calculus. Today I'm going to work through just a few sample problems from the textbook. Those are listed here at the top of the page, 1, 2, 10, 14, and 42. Numbers 1 and 2 are more of a vocabulary review and some basic information that we need to be aware of as we move forward with these trigonometric functions. In each part, A through C, in part number 1, question number 1, we must identify the domain and range of our inverse trigonometric functions. Now the thing to remember here is that the domain and range are switched compared to the original trig functions. And we talked a little bit about this on Tuesday, that if I draw a unit circle and I consider the sine function, only the values from negative pi to positive pi would be necessary for us to obtain all output values for that function. So in this case, since all that I needed was an input between negative pi over 2 to positive pi over 2, and that would produce all possible range or result values, then I want to switch that here. The inputs or domain for this function would be any number between -1 and +1, since those were outputs or ranges from the original sine function. And the range of our inverse sine would be negative pi over 2 to positive pi over 2. So in other words, we should only be able to input numbers between -1 and 1 into the sine inverse function, and we should only see results that exist between negative pi over 2 and positive pi over 2. Similarly, when we consider the cosine function, if I had a unit circle here, then only the inputs from 0 to pi would be necessary in order for us to obtain all unique range values or output values for the cosine function. Those output values for cosine existed between -1 and 1 also, so those would act as the domain or input values for the cosine inverse function. And therefore, too, the output or the range of our cosine function would be the input for our cosine function. So maybe I said that wrong. The cosine inverse has a range of 0 to pi because the regular cosine has a domain of 0 to pi. And lastly, when we consider our tangent results, again, we can achieve any unique tangent result as long as we input an angle measure between negative pi over 2 to positive pi over 2. Any angle measure in this area here would return all possible values for our tangent function. The only catch is that if I were to use the point at the very bottom of this unit circle and the very top, if I were to use the point 0, -1, or 1, 0, sorry about that, not 1, 0, but 0, +1, if I used either of those points to generate a tangent calculation, remember we have a problem here because that should be y divided by x. Those results are undefined. So as far as our domain goes, we can input any real number into this tangent function because the output of our original tangent function would be any number from -infinity to +infinity. We can get to larger and smaller infinities by picking angle measures that are closer and closer to these two endpoints. However, the range of our inverse tangent function has to be the domain of our original. And we said we can run from negative pi over 2 to positive pi over 2 and obtain results. We just can't include those two in our endpoints. In question 2, we're asked to identify the arcsine, arccosine, and arctangent of our theta measurement here. Now we're used to using a regular sine, cosine, and tangent measurement, And if we were to use the sine function here, we'd have to consider the opposite side and the hypotenuse. So sine of theta would be equal to 8 divided by 10. Therefore, sine inverse of 8 divided by 10 would be equal to theta. And this is the fraction that we're looking for our answer over here. Similarly, for cosine, we would deal with the adjacent side and the hypotenuse. So we're going to use the number 6 and 10. And lastly, for tangent, we would use the opposite side and the adjacent side, 8 divided by 6. Pay close attention though, because you'll notice that the fraction of the side lengths is now inside the trig function instead of being the target of the result of our trig function. These inverse functions allow us to calculate unknown angle measures, whereas our traditional trig functions allow us to calculate side lengths. Now you may also notice that these fractions can be reduced. So if you were to write a solution sine inverse of 4/5 or cosine inverse of 3/5 or tangent inverse of 4/3, then any of these would be appropriate solutions or answers to this question as well. Let's take a look at number 10 and number 14. The instructions in the textbook ask us to use a calculator to find an approximate value of each expression rounded to 5 decimal places. So in this solution here, sine inverse of 1/3, well, keep in the back of your mind that this is really asking us to find some theta, some angle measurement, so that sine of that angle measurement is equal to 1 divided by 3. Or in other words, we're trying to create a right triangle here whose opposite side is 1 and its hypotenuse is 3. We're looking for the theta angle measurement that would make that happen. So we can use a calculator to solve this, though, since 1/3 is not a typical fraction that we would see in our unit circle. So when I switch over to the graphing or to the calculator here, I'll call upon the sine inverse function, and we'll write the numbers 1 divided by 3 to find sine inverse of 1/3. If I press Control Enter, that will give me a decimal result. So 19.47122 looks like a pretty good answer. Theta is equal to 19.47122. Now my calculator is set in degrees right now, so this theta measurement is 19 degrees. Suppose our calculator asked for, or suppose the textbook asked for the question returned in radians. Well, we need to make that change happen then. So the way I would do that is I'd press the home button and jump over to the settings here, adjust the document settings instead of reading degrees to say radians, and I'll press OK. I'll go back to the current document and press Control Enter again, and now that same calculation is repeated, only now my result is returned in radians. 0.33984 looks like a good result measurement in radians. So 0.33984 radians. And the textbook doesn't really say whether to use degrees or radians, so if I were to ask the question on a quiz, I would clarify that for you, whether I want the result in degrees or radians. Now for number 14, we need to solve this problem. In essence, we're looking for a sine function of some angle measure so that the result is equal to -2 divided by 1. And this should throw up a red flag for you because in essence this is asking us to find the angle measure of some right triangle in such a way that the hypotenuse is the opposite side is equal to 2, but the hypotenuse is equal to 1. We know that this cannot happen because the hypotenuse is supposed to be the longest side. That would not be the case in order to have a sine value equal to -2. So we can answer this as undefined. Also note that the input or the domain values for sine we just discussed a moment ago are any numbers between -1 and +1. The number -2 does not fit in the domain, therefore we know right away that this answer is undefined. And that's a good explanation as to why. The right triangle associated with that number simply does not exist. Number 42 is a good question to ask. It talks about a real world issue that we might face and how we can use trigonometry to work through it. These figures below indicate that the higher the orbit of a satellite, the more of the Earth the satellite can, quote, see. Let theta, s, and h be as drawn in the figure and assume that the Earth is a sphere of radius 3,960 miles. So here's what we're trying to show you here, that if the height of this particular satellite is only this distance, we can only see this portion of the Earth, or we can only service that portion of the Earth. However, if we increase the height of that satellite, we can now see a larger portion of that Earth. Now what happens is this sight line that's formed creates a right angle with the edge of the Earth. This is what's called a tangential line, or a tangent line. It always forms a right angle against a circle like this. And we were told that the radius of the Earth is 3,960 miles. So the total height of the satellite from the center of the Earth would be h plus 3,960 miles. So 3,960 miles plus h is the length of our hypotenuse, and 3,960 is the length of our adjacent side. So with that information, we can answer part A. Part A asks us to express the angle theta as a function of h. Well, we know that cosine of theta is equal to the the adjacent side, which is 3,960, divided by the hypotenuse, which was 3,960 plus h. Now, if we need to express the angle theta as a function of h, then we need to solve for theta, or get theta by itself. So theta would be equal to the inverse cosine, or arc cosine, of that same fraction, 3,960 divided by 3,960 plus h. Now part B can be answered with a formula that was shown in the textbook's chapter, but we really haven't talked about it in class. We can find the distance s. S is the distance, the length along this curve, by using the formula s is equal to radius times 2 times our included angle, 2 times theta. So in this case, the distance s is equal to 3,960 times 2 times our included angle measure, which we haven't actually identified yet. We have to still call it theta. So the distance would be equal to 7,920 times theta. Once we identify theta, we can then calculate that distance in terms of miles. Now, since we've identified theta in terms of h, as we've shown with the function above here, we can write this distance slightly different. We can say that the distance s is equal to 7,920 times the cosine inverse of 3,960 divided by 3,960 plus h. That way, the only measurement that we need here is the height of the satellite above the Earth, rather than needing the theta angle measurement itself. It's much easier to identify the height of the satellite above Earth than it is to identify the angle measure theta created here from the center of the Earth. So now we can use this calculation. S is equal to 7,920 times cosine inverse of 3,960 divided by 3,960 plus 100. Since part D is asking us for the total distance S that can be seen by the satellite when it's 100 miles above Earth. And I've set up that calculation in the calculator here. 7,920 times cosine inverse of 3,960 divided by 3,960 plus 100. Oops, let's get an approximate result here. So the number is 1,761.4593. Let's go ahead and round that to 1,761.5 miles. 1,761.5 miles. And lastly, if we had a specific distance in mind, we wanted the satellite to view both Los Angeles and New York. If they're 2,450 miles apart, well, we can solve for that solution. Our answer should be 2,450, and our job would be to find h by itself. So we have 7,920 times the inverse of cosine 3960 divided by 3960 plus h. So we get to use some algebra skills here in order to identify h. I would start off by dividing both sides by 7920. So we have 2450 divided by 7920. That's going to equal cosine inverse of 3960 divided by 3960 plus h. Then I want to undo the cosine calculation here, this cosine inverse. So I'll apply the cosine, our traditional cosine rule, to both sides. Now this really isn't the appropriate method to show, but this is more or less a side note reminding me that I've applied the cosine to both sides of the equation. Really what we should show is that cosine of 2,450 divided by 7,920 is equal to 3,960 divided by 3,960 plus h. From here, I would probably use the technique that I remember from algebra class, which kind of abbreviates our cross multiplication technique. This entire side of the equation can be replaced with this side, or this denominator value. Those two pieces can switch positions. So I know that 3,960 plus h is equal to 3,960 divided by cosine of 2450 divided by 7920. And lastly, I can subtract both sides by 3,960, and that'll isolate h for me. 3,960 divided by cosine of 2450 divided by 7920 minus 3960. That should solve h for us. This is something that we can go to the calculator with now. And now that I have that entered into the calculator, we can press enter here. Whoops, let's get an approximate result. Oops, I had a typo in there. Let me come back up here and adjust this. This value should have been 7920. Let me recall that calculation. We'll jump into the calculator here. 7920. There we go. Now let's see our decimal result. 197.3. That seems a little bit more realistic. The satellite should be 197 miles above the Earth rather than 901. That seemed a bit too large. So 197 is a good answer for this. So height is equal to 197.3 miles. And again, I recognize that first answer was way too large, especially since just a moment ago when we were 100 miles above the Earth, we could see 1,700 miles. We shouldn't have to travel another 800 miles just to see our sight line of 2,000 miles. So this is really an exercise in algebra at this point. We set up the trig function this way, and it was our objective to solve for h. And it took quite a few algebraic steps in order to get there. Hopefully you were able to follow along, and I hope that you can repeat something similar to this in the future. Please let me know if you have any questions as we move forward.